Okay, so up to previous class we have discussed the things related to strain and stress, and particularly we have understood also the strain behavior of mild steel and what are the different salient points in a mild steel stress strain curve. We also understood that when there is not a perfect yield point, then how to find out the yield point? Okay, using the concept of method of offset and the proof stress concept, right? And third thing we have also learned, that is what is actually factor of safety and what is allowable stress and what is working stress. On top of that, previous class we have also learned about strain energy concept and because of linear extension or compression, how much will be the strain energy and what will be the resilience, that we have also understood. Okay? So now in today's class we will try to understand what is another one type of stress, that is shear stress. So what is shear stress? So shear stress, you see, suppose I take a block like this, okay? Or you take, suppose if you put your hands like this and if you try to slide one over the other. So like the frictional force, there will be a force getting generated at the interface of the two surfaces, right? So that interface generated forces, whatever force will be getting generated. So internally, when the push is there, when the sliding intention is there, at that time, there will be an internal resistive force also getting generated. And when we get that internal resistive force, if we divide it by the area on which that resistive force is acting, we will get the stress. And that stress will be termed as shear stress. Right? So, if you try to understand diagrammatically, then what is happening? You see, there is a body something like this, and inside that is, let's say, ABCD. There is an element, okay, and a force P is acting in the parallel and opposite direction. Try to see. If you put your hands together like this, so if I am pushing my hand in this way, the other will be pushed in this way. So this is what is the nature from where you will get the shear stress. So the force is acting, you can observe, here P is acting, here another P is acting. So 2P, same P force, it is separated by a distance and they are parallel to each other. Okay? And when this kind of force is acting, then there is a resistive force getting generated at a plane, let's say x plane if I take x plane, in that plane there will be a resistive force getting generated, and we have seen similar to the linear strain concept or linear stress concept. What happened? If I put a pulley with a P, then there is a resistive force R getting generated. In this case also, at the interface there will be a resistive force R getting generated, and that R will be equal to the P. And that's why we call the shear stress tau, we denote it with a symbol called tau, it is equal to P by U. What will be the unit? Unit will be same as the direct tensile stress, that is Newton per meter square. Here also you should understand, I told you that you must have clear concept about what is megapascal, what is pascal, what is gigapascal, all these stuffs. Okay? Because unit conversion is very, very important. Clear? Now if you see, similar to the direct tensile stress, in the shear stress, I want to find out a very small point, or if the stress varies from one point to other. Let's say if I have a rectangular block like this and I am pushing it like this, then there will be similar kind of stress getting generated, equal kind of stress getting generated on that plane. However, if I take the shape which is uneven in nature, and if I try to push the body, right, with the two parallel forces in the each and opposite direction, then what will happen? So each and every plane will have different kind of stresses getting generated. So how to find out the stress at a particular point? This is a very important concept. Later on, you will see in your higher studies when you go, you will see this differential concept of stress understanding becomes very, very important. Okay? So differential concept means very small area, in a very small area, let's say delta I, if a very small amount of resistive force delta P is getting generated, and when the area is tending to 0, that means area is becoming infinitesimally small, very small area. Okay? So delta A, limit delta A tends to 0, del P by del. Have you understood? So this is what is actually shear stress. And when this delta P is becoming, because of the two equal and opposite forces acting in the parallel direction, then only it will be called as shear stress. Is it clear? Now you see, there is a very interesting concept you can say in case of shear stress. What is that concept? The concept is, you see, suppose I am pushing I am putting the body under these two equal and opposite forces, right? So you take any body, let's say I take this duster, okay, and I am pushing it in equal and opposite direction forces. So one force is getting in this direction, other force is getting in this direction. So what will happen? Because of this, you see there will be a couple getting generated. Couple, you understand? Two equal and opposite forces act separated by a distance. So how much will be the value of the couple? Force multiplied by this distance. So when there will be a couple, there will be a tendency to rotation. So there will be a twisting kind of thing will be happening, right? However, you see, we are studying strength of material, so material of deformable bodies, and we are considering the body must be under equilibrium. So how the body will remain under equilibrium? If two equal and opposite forces are acting like this, then obviously there will be a couple and tendency of the body in the body moving in this direction, right? So to resist this, there should be equal and opposite couple coming from the opposite direction. Correct? So if I am pushing a body with a parallel force in this direction like this and in this direction like this, equal and opposite. So to counteract these two forces, there must be another forces coming or another stresses coming inside the body, which should be, if I am putting it like this, if I am pushing it like this, right, or opposite and equal, so this way, right? So if it tends to rotate in this direction, right, so that should be opposite directional force, so there should be another one force in this direction and this direction. Have you understood? And this interesting concept in case of understanding of shear stress is termed as complementary shear stress. Complementary shear stress. So take this example of this body. Everyone can see this body. So you see there is a small body ABCD, okay, cubical kind of separate body. Now we are considering it in two-dimensional space. If we take it in two-dimensional space, then you see very important thing you should understand. This body is three-dimensional. X, Y, Z planes are there. Okay. Now if you see, if a stress is acting in this direction, tau is acting in this direction. Okay. So there will be equal and opposite tau coming in this way. So if I come to this two-dimensional space, then you see there is a tau xy acting in this direction. So equal and opposite tau xy will be coming in this direction. Because equal and opposite forces are happening. Area is same, I am dividing it. So this will create a couple to rotate it in this direction, isn't it? It will rotate it in this direction. Arrow is in this direction, arrow is in this direction. So how it will rotate? It will rotate in this direction, right? So to counteract it, there must be an equal and opposite force which will be occurring in this direction. Got it? So you see, this tau yz, this tau xz is in this plane and tau yz is in the other plane. Other plane means perpendicular plane. You try to understand that. It's a perpendicular plane to the xz plane, right? So there is another stresses coming in the perpendicular plane which will be counteracting this couple on the xz plane. Have you understood? And this strain, these two stresses will be termed as complementary shear stress. Have you understood? And now, as you understand now that body must be in equilibrium, so what should happen? So tau xj, which is separated by distance y, correct, should be equal to tau yz or tau dash yz, whatever you say, tau yz into x. Correct? Now you see this x and y are same because I have taken a very small body. That means my tau xj should be equal to tau yz. Right? So how it is coming, you understand? So tau must be equal to tau dash. That's what I have written here. Tau must be equal to tau dash. What does it mean? You see, it shows that every shear stress, ऐसे हो ही नहीं सकता, कोई भी shear stress, complementary shear stress के बिना आ ही नहीं सकता. Everywhere you get a shear stress, there must be a complementary shear stress. Otherwise, the body will not be under equilibrium. Have you got it? So every shear stress is accompanied by an equal and complementary shear stress. And what is that equal? What is the complementary shear stress? It is the shear stress generated by equal and opposite parallel force acting in the other direction. And in which direction? Right angle to the original force direction of the shear. That's why I have written planes at right angles. Have you understood the complementary shear stress concept? Is it clear to everyone? Here you see the notation wise, if you see, if this is having this arrow in this direction, the other phase the arrow will be in this direction. That is what the last sentence says. Because when there will be opposite couple, it will be coming like this. Clear? Now considering this shear stress concept, let's try to understand shear strain. And what is shear strain? So obviously if there is a stress, there will be strain. And which is coming first? Actually deformation is coming first, then stress is getting generated. So shear strain actually measured in terms of angle. Try to understand it. Shear strain, because of shearing what happens? Because of shearing, what happens? Actually the plane or the body, it tries to shift in an angular direction from its original position. Okay? So if I take the same body ABCD, the small part of that, a big body, if I cut it from that and I take a small portion ABCD, then how do you understand shear strain? You see, there is the equal and opposing force acting. So tau is acting in this direction or tau dash is acting in this direction. So equal and opposing forces, opposite shear stresses. And you can see the body is deforming in this direction and it is from its original position, it is making an angle phi. Okay, it is making an angle phi, right? And when it is making an angle phi from its original position, where is the body's original position? This vertical, this was initially vertical, right? After it is sheared, then it changes its original position and it sits by some amount of angle. So that is actually phi. Now this phi will be defined as the shear strain. This phi angle will be defined as the shear strain. Now how do I find out phi? So you see the shear strain is actually delta L by L, and actually it is not phi, you can say it is tan phi. And when the phi is very small, tan phi becomes equal to phi. What is the value of tan 0? Sin 0 is 0, cos 0 is 1. So sin 0 by cos 0 is tan 0. So tan 0 is equal to 0. So when the value of tan is very small, tan theta is very small, then theta becomes equal to tan. Many cases in civil engineering, structural analysis and strength of materials, everywhere, many cases when the deformations are very small, when the angular deformations are very small, this assumption will be taken. But when theta is very small, the tan theta value will be considered as equal to 2. Okay, where theta is in radian. Okay, now you can understand now what is shear strain. So shear strain is equal to gamma we have defined it as gamma is equal to tan phi, which is nothing but equal to delta L by L. So initially this is the length of the body L, and it has deformed by an amount delta L, and delta L is a shift, and because of that there is an angle getting created phi. So how much will be the tan phi? Tan phi will be delta L by L, and that will be equal to the shear strain. Have you understood? So this is actually the basic concept of shear strain, and from this shear strain you get another one, modulus, because Hooke's law, within the limit of elasticity, Hooke's law is valid. So in case of shear stress also Hooke's law is valid, and shear stress will be directly proportional to shear strain within the limit of proportionality, right? So that's what when you do, and the limit of proportionality, when you are saying there will be a proportionality constant, and that proportionality constant will be termed as modulus, and that modulus will be termed as modulus of rigidity, and that is termed as G. So G is nothing but your tau by phi, which I can write tau by here. And what will be the unit of shear strain? The unit of shear strain will be nothing, because it is a dimensionless delta L by L. So it is stress by strain. Modulus of rigidity will have unit exactly equal to the stress. However, shear strain will not be having any unit. Here, have you understood modulus of rigidity? Now from this we try to understand another one definition, which is called Poisson's ratio. What is Poisson's ratio? In physics you have studied, right? So what is actually Poisson's ratio? Poisson's ratio, you see, very simple to understand. Suppose I pull something, extending, okay? So when I am extending it in the longitudinal direction, there will be contraction in the lateral direction. Got it? Longitudinal direction extension means lateral direction contraction. On the reverse way also, if I compress the body, then it will be longitudinally shortening and laterally expanding. Both can be explained with Poisson's ratio. So what is the Poisson's ratio? Poisson's ratio is thus that defined as it is the lateral strain by longitudinal strain. So body, when it is put under a longitudinal force, or let's say direct tensile stress or direct compressive stress, then what happens to the body? There is an extension, and because of that there will be longitudinal strain coming, which is nothing but equal to delta L by L. So because of the longitudinal strain coming into the body, there will be also little bit shortening of the lateral dimension, and if the lateral dimension shortening is termed as delta B, and the original lateral dimension is B, then delta B by B, that will give you lateral strain, and the ratio of the lateral strain to the longitudinal strain will be termed as Poisson's ratio. Have you understood it? Is it clear? Yeah? Take this example. So you see, there is a body P, there is a body like this, which is having length L. I am putting it under tension. So P is the force. There is an extension of delta L. So when I am pulling it, you see, there will be contraction on this side. So let's say this dimension is delta B. Come over here. Okay? So let's say this dimension is delta B. So what happens? If this dimension is B, there will be a little shortening in this direction. Let's say that this shortening is delta B. So if this shortening is delta B, then this delta B by B will be your lateral strain, and delta L by L will be a longitudinal strain. And what is Poisson's ratio? Poisson's ratio is nothing but the ratio between lateral strain and longitudinal strain. Okay? And you see that it is a constant ratio. Okay? It is a constant ratio. So you see, it's not like that if I take different kinds of length or different kinds of cross section, I will get different Poisson's ratio positive. Got it? So depending on the load, it remains constant. It is a material property. You must understand. Poisson's ratio is kind of a material property. Okay, it's not like that. If I am taking a longer dimension of the bar and shorter dimension in the shorter cross section, in that case my Poisson ratio will change when I take a shorter dimension of the bar and more cross section area of the bar. Okay, so Poisson ratio is the material property and this ratio is constant. Okay, so this ratio constant is very important and this will be also used in many cases in your strength of materials as well as structural analysis for analyzing many of the things. And this is a very interesting concept. I will be discussing it today only. The generalized Hooke's law when you will be understanding. We have understood Hooke's law in terms of stress is proportional to strain. But when we are considering generalized Hooke's law, I will come to that. Generalized Hooke's law. What is it? Okay? Then you will understand what is the importance of this Poisson system. Okay? Now you see, I have given small two examples. You can see it later on. And this expression is very important. You use it in soil mechanics also. Okay? Use it in soil mechanics also. When you will be doing compression tests of soil and what is called triaxial testing of soil. Correct? Unconfined compression testing of soil. Okay? So you see, this is a beautiful concept where you will observe that the Poisson ratio is delta B by delta L by N. So you see, this is nothing but mu into E. So delta B by B, delta L by L. So delta B by B will be what? Poisson ratio multiplied by longitudinal strain. That is nothing but small exercise, right? Now, if I take the other direction, you see when I am pulling it, if it is a rectangular cross section, right? If it is a rectangular cross section, in both the dimensions it will shorten. Correct? So let's take if I pull it like this on both directions, then what will happen? On this direction also it will shorten. On this direction also it will shorten. Correct? So in the B direction it will shorten. In the H direction also it will shorten. So if I now try to calculate the modified area because of the extension put, okay? Well, because of the extensional put, then modified area will be nothing but because you have shortening in both the direction. So in the breadth direction, let's say it is delta B, height direction it is delta H. You just multiply it, you get the new area. So you see, you will get a BH term, you can take it common and you have BH 1 minus delta B by B and 1 minus delta L by B. If you take common B, if you take a B out from here, you will get 1 minus delta B by B. If you take H out from here, you will get 1 minus delta H by B. And what is delta B by B? Delta B by B is nothing but nu into itself. Correct or not? Similar to that, delta H by H will be also nu into itself. So that means your new area will be equal to original area multiplied by 1 minus mu into epsilon whole square. This is a very important formulation from the Poisson ratio. You will be using it in your soil mechanics. You will be using it many other places also. So when you will be studying about the shear strength of soil, okay, and when there will be compression in a direct compression test, okay, there will be shortening of the body in the one direction and there will be expansion in the body in the other direction. So when you will be calculating the stress, in many cases you have to calculate the stress in terms of this ANU, and this ANU will be, you can obtain using A into 1 minus mu epsilon. Got it? Clear? So next slide, let's move to the next part. So that's what I was focusing on just a few minutes back. I told you the generalized Hooke's law, very important. Okay, you must understand it clearly. Okay, if you go to GATE and engineering services kind of exam, this generalized Hooke's law is being focused on, and it's a very simple concept. You should try to understand it just from the formulation. I'll explain. See, what is generalized Hooke's law? Actually, you see, suppose I take a body in a three-dimensional space x, y, z, and there are three mutually perpendicular stresses acting on this body. So mutually perpendicular stresses acting on this body means I am pulling the body in this direction, I am pulling the body in this direction, I am pulling the body in the other direction. So x, y, z, all the three directions I am pulling the body. So if I pull it or if I compress it, if I pull it in one direction, if I press it in another direction, so the body's nature of deformation can be explained using generalized Hooke's law. What does it say? It says a simple thing, that whenever there is an extension in one direction, there will be compression from the other two directions. Whenever there is a compression in one direction, there will be an extension in other two directions. And that's what will be coming into picture in case of generalized Hooke's law. Okay? So you see, what is happening when you are pulling the body in X direction? Please try to understand. Very simple concept. Formula mark for. If we are pulling the body in one direction, correct? So there will be extension. So I can explain it using normal Hooke's law. Correct? Now you see, when there is an extension in this direction, the body is subjected to mutually perpendicular forces. So if I am pulling the body in the other direction, what will happen? The direction where I have applied the pull, in that direction also there will be some compression. Hoga ki nahi hoga? In the Z direction I am pulling it. So in this direction there will be some compression. Hoga ki nahi hoga? So actually if you understand, Poisson's ratio comes into picture. So lateral in the longitudinal elongation, and because of the mutually perpendicular stresses acting in the other faces of the body, there will be lateral compressions, and that's where the strain will change. So the strain in the X direction thus will be coming sigma X by E. So if I only consider sigma X, the effect of sigma X, so what will be the strain? What will be the strain according to Hooke's law? Stress by modulus of elasticity. So strain will be sigma X by E. Correct? Now you are applying the body under a generalized three-dimensional perpendicular stresses. So what will happen? If I am pulling it with sigma X, okay, this direction will to accelerate ho gaya bottom. But there is a force acting in the Y direction also. So because of the Y direction pull, there will be a shortening. How much shortening? It will be explained in terms of nu, Poisson's ratio. Right? So the Poisson's ratio, if I apply, then you see it will become nu into sigma Y by X. Why nu into sigma Y? What is nu? Nu is your delta L by L by delta B by D. Right? So if I consider that nu, you see nu in terms of the stress, if I try to understand. So the how much will be your delta L by L? Delta L by L is nothing but nu into epsilon. Right? So what is epsilon? Epsilon is nothing but sigma X by X. Right? So actually what is happening, you see, whenever there is a direct pull in one direction and the pull in the perpendicular direction pull is in the perpendicular direction, in that case your strain will be equal to mu into sigma Y by T, and that will be a shortening. That's why the minus sign is there. Have you understood? So if there is three mutually thing, so because of Y there will be shortening, because of X directional stress there will be shortening. Z directional stress there will be shortening. So if you remember this, you can write other two also. There is a similarity in the equation or not? Similarity hai? Okay? So now my question here will be, who can answer? Let's see. Suppose I put this sigma X with a pull. I do sigma X with a pull, and I tell that sigma Y and sigma Z are compressive stresses. Then how does generalized Hooke's law change? क्या चेंज मिलेगा, क्या परिवर्तन आएगा? Sigma X I am putting it with a pull, and sigma Y and sigma Z I am compressing it. I am giving a compressive stress. What will change in the general form? So compressive stress, what will happen? This sign will become plus, but not everywhere it will become plus. Please try to understand. Not everywhere it will become plus. सिग्मा एप्सिलॉन x के लिए ये प्लस बन जाएगा, But when I go to epsilon y, sigma y by E will be there. But sigma z by sigma z into this will be plus. However, sigma x into mu will be minus. Have you understood? Have you understood or not? So if there is a composite, how will you understand that how to write the generalized part? So if there is a tension, you put it plus. If there is compression, put it minus. And when there will be minus, nu into sigma x or nu into sigma y, nu into sigma z, put a minus sign before. Have you understood or not? Clear? Very important concept, generalized Hooke's law. Okay? गेट एग्जाम में जनरलाइज या स्ट्रेस स्ट्रेन का प्रॉब्लम बहुत आता है. ओके, एनी कॉम्पिटिटिव एग्जाम इफ यू गो, प्रॉब्लम कम्स यूजिंग दिस फॉर्मुलेशन. ओके, so now you see the volumetric strain. I am going to another one concept called volumetric strain. Let me take. So volumetric strain. What is the volumetric strain? Okay. So volumetric strain means change in volume. Let's say I am pulling the body with sigma x, sigma y, sigma z. What will happen to the body? Body will have change in volume because in each and every dimension there will be shortening or elongation of the body, right? So there will be change in the volume of the body. Correct? So the change in volume divided by the original body volume, that will be defined as volumetric strain. Very important concept. From there we will be coming to another one modulus, which is called bulk modulus. So we must understand volumetric strain first, then we will go to bulk modulus concept. Okay. So now volumetric strain is a concept where, because of the mutually perpendicular acting forces or mutually perpendicular acting stresses, when the body goes for a deformation and its volume changes, the change in volume of the body divided by the original volume will be defined as volumetric strain. So now if I take a body with a dimension of small I, small j, and I put it under three mutually perpendicular forces, this sigma x, sigma y and sigma j, then what will be the change in volume? So original volume of the body will be having x, y, z, it's a cube, or let's say it can be anything like parallelepiped shape. Okay, so if it is cube, then x into y into z. Okay, if it is having x, y, z dimensions are different, then it will also be having volume x, y, z, right? A into b into c, right? So x into y into z. So this is my original volume. So delta b is how much? Delta b is increase in volume. So what will be the increase in volume or what will be the decrease in volume? So increase in volume, let's say if I am pulling it, then increase in volume will be x into. So originally the side was x. So how much will be it after the extension? After the extension it will be x into epsilon x. Okay, because what is strain? Delta L by L is equal to epsilon x. If you understand it in simple term. So in the x direction strain, which is coming from the generalized strain, right? So that is how much? That is equal to epsilon x, and x direction strain, if I multiply it with the original length, what I get? I get extension. Delta L by L is equal to epsilon x. So what will be the value of delta L? Delta L will be epsilon x into L. Now when L is equal to x, then epsilon x is equal to delta L is equal to epsilon x into x. So same way I have written it, x into 1 plus epsilon x, y into 1 plus epsilon x, z into 1 plus epsilon x. So now if I simplify this equation, I keep it to you, simplify this equation, you will get this common x, y, z will be multiplied, you can get a common out over here. And if you multiply these terms, 1 plus epsilon x, 1 plus epsilon, 1 plus epsilon j, you see, you will get many terms. So this 1 and 1 will get cancelled after multiplication. Okay? And you will get many terms in terms of epsilon x, epsilon y, epsilon j. And you will get terms like epsilon x, epsilon y. You get epsilon y, epsilon j. Okay? And also you will get one term epsilon x, epsilon y, epsilon j. However, you see, epsilon x, epsilon y, epsilon j, all are very small amount. They are strains, right? It will be how much? Let's say 0.01, 0.001, right? 0.02% strain. उस दिन देखा था ना प्रूफ स्ट्रेस. So 0.02% strain का मतलब क्या है? 0.2% strain. 0.2% strain जो देखा था. So 0.2% strain means 0.002. So 0.002 multiplied by 0.002, how much it will come? 0.00004. So it becomes lesser number, right? Very small number. So that's why these terms, whatever is being multiplied, epsilon x, epsilon y, epsilon j, such kind of terms, or epsilon x, epsilon y, epsilon j, that will become more smaller. So all these terms we are neglecting. All these terms we are neglecting. And if you neglect it, you will get a very simplified term of getting the volumetric strain. Okay? So you see, epsilon x, y, z you have taken common, so it will be cancelling out top and bottom, and then you will get a very simplified term which will come epsilon x plus epsilon y plus epsilon y. That is volumetric strain when a body is subjected to mutually perpendicular forces in three directions and direct tension or direct compression kind of forces, then volumetric strain can be defined as epsilon x plus epsilon y plus epsilon j. And these epsilon x, epsilon y, epsilon j all should come and all must come from generalized Hooke's law, not from Hooke's law. Direct Hooke's law you cannot apply. It must come from generalized Hooke's law because mutually perpendicular direction force, whenever it is acting on a body, then what happens? If one direction there is a tension, one direction there is an extension, on the other direction there will be compression. Got it? So this is very important to understand. So generalized Hooke's law, please carefully read it. Okay, it's very simple. Practice it rather. Okay, write it and practice it. So you see, this is the volumetric strain concept. So epsilon x, epsilon y, epsilon j, and you see inside this epsilon x, epsilon y, and epsilon j, the Poisson's ratios are also included because from the generalized Hooke's law you can see Poisson's ratio are included inside this. So that's why you need not to worry about Poisson's ratio over here. Poisson's ratio is already included. So one of the explanations in the report I have asked you regarding this. So very carefully read it, okay, and try to attempt that. Okay. Then you see the more definition bulk modulus. Now I am coming to bulk modulus. So I said that volumetric strain you need to understand first, and then you go to understand the bulk modulus. And what is bulk modulus? Now you see there is a little change from the volumetric strain. I am coming over here. So when we are defining the bulk modulus, you see there is a small change I have done from the previous figure. In the previous figure you see I have written sigma x, sigma y, sigma j. Sigma x, sigma y, sigma j may be different in dimensions. May be different in values, right? Now when this sigma x, sigma y, sigma j all becomes equal, and let's say they become equal to p. Okay? So when a body is subjected to three identical stresses, in the previous case we haven't considered identical stresses, right? Here we are telling, when defining the bulk modulus, we should understand that body is subjected to identical stresses. What does it mean? Identical stresses means all the three directions, same forces are acting. And let's say sigma x equal to sigma y equal to sigma z equal to p. Now, if such kind of force is acting on the body, then the bulk modulus will be defined as K is equal to P by epsilon P, where P is the stress or the identical stress which the body is subjected in the three directions. Where does it come? When you put a body inside the water. So hydrostatic pressure is acting, complete submerged body, right? And all the three directions, same forces will. So that is compressive in nature. So if it is a compressive in nature, then this value will change to minus. The stress value P will be changing to minus. Correct? So modulus of bulk modulus, you have understood what is bulk modulus. Now from this bulk modulus concept, now let's try to have an equation established between bulk modulus and relation between, what is the relation between bulk modulus and modulus of elasticity? Very simple. So bulk modulus, what I have said? So we have said that epsilon x equal to epsilon y equal to epsilon z. Because if in all direction P is acting equal, identical, then your epsilon x, epsilon y, epsilon z all will be equal, right? So if I take that and if I apply the generalized Hooke's law over here, so what I do? If I go back, see generalized Hooke's law if I do, so epsilon x will become what? 1 by E P minus mu P plus P. So it will be 2P. So minus 2P mu, here it will be P. So that's what is being written over here. From the generalized Hooke's law it is coming. So I am taking P out. So P by E is taken out and epsilon x will become equal to P by E into 1 minus twice mu. Is it clear? Okay? Coming from generalized Hooke's law. Now, what is volumetric strain? Volumetric strain is nothing but epsilon x plus epsilon y plus epsilon z. But epsilon x, epsilon y, epsilon z, all three are equal, isn't it? So if all three are equal, I can sum it up. So I get a volumetric strain E, epsilon g. So epsilon x plus epsilon y plus epsilon z, I sum it up. So if I sum it up, what I will get? P by E into this, P by E plus P by E into this, plus P by E into this. So I get 3P by E into 1 minus twice E. I will get it or not? Now what is volumetric strain? What is bulk modulus? Bulk modulus is nothing but volumetric strain by bulk modulus is equal to P into EV, or I can write EV is equal to P by K, right? So I am writing EV equal to P by K. So if I write that, so I get an equation. So 3P by E 1 minus twice B twice mu. If I put this P by EV over here, so EV's value I am putting. What is the value of EV? Value of EV is P into P by K, right? Here I can put P by K. So PP cancels out. So what I get? And K goes up. So I get 3K into 1 minus twice. This is the relation. You might have studied it, but how is it coming? You might not have studied in your strength of materials, whosoever is coming from the background of diploma. Right? You understand how it is coming? Very simple relation. Okay? So this equation is very important. Okay? This equation is very important. You should remember it. Okay? You should remember it. And elastic constant. So there are three elastic constants. Modulus of elasticity, shear modulus, bulk modulus. Okay? So modulus of elasticity, shear modulus and bulk modulus, these are called elastic constants. And very important note I have given here, the Poisson's effect. Please try to understand, this is very important. This is coming from generalized Hooke's law actually. The Poisson's effect is already there inside epsilon x, epsilon y and epsilon z, considering the generalized Hooke's law. If you do not consider generalized Hooke's law, you will be doing a mess in your calculation. Okay? So there are problems given, conceptual concepts given in your report writing regarding this. Okay. Now coming to the other relations, so there are another two important relations. So one relation is E is equal to 3K into 1 minus twice mu, and another one relation between modulus of elasticity and shear modulus. The derivation of this is very complicated. I will not say complicated. I will give you the derivation also in a separate handout. You can see, but the relation between modulus of rigidity and modulus of elasticity is twice G into 1 plus mu. Now, from this, I can derive a relation between all the three moduluses. Modulus of elasticity, modulus of rigidity, and modulus of what? Modulus of bulk or bulk modulus. So if I do it, how do I do it? Simple, I have done. See, I have done E 3K 1 minus twice mu. I have multiplied this. So here I have made it twice G 1 plus mu. So 2 into 1 plus 2 into 2 mu. So cancel it and then you get another one relation. So your relation will come E is equal to 9GK by 3K plus G. So all these three relations are very important. You must understand it. Okay, कुछ मिस्टेक है क्या यहाँ पे? E by G, what I have done? E by G, I have divided E by this G, and I have taken this 2 inside this. So I have written 2 plus 2 new, and this I am adding it. So 2 plus 2 new minus 2 new cancels. ওই যে কি একটা বলে না অপনয়ন পদ্ধতি বাংলাতে বলে I don't know what is the English term हमने तो बंगाली में पढ़ाई किया ठीक है অপনয়ন ओके তাই তো বলে হ্যাঁ অর্জমূলন তো নয় অপনয়ন রাইট so you are just cancelling it right plus 2 new minus 2 new cancel correct so now you get this relation. So I think I have exceeded my time. So I hope that you understood up to this point. Is it laboratory class or theory again? So now there is another one derivation is given stress in terms of strain. Okay, go through my handout. Every minute steps is being done. And this is a very important relation stress in terms of strain. And here you get another one constant you will find, you just go through. If you do not understand, I will explain. It is nothing but complete mathematical derivation and step by step I have done it, hand calculation करके उसको scan करके इधर डाला. Okay? And if you get it, you will get a constant like lambda. Okay? There will be a constant coming lambda, okay? And this lambda, you see the equation, stress in terms of strain, you see? We have understood strain in terms of stress in case of generalized Hooke's law. From that, we are reversing it to find out stress in terms of strain. Very important, okay? Many questions come in competitive exams regarding this, okay? And you get a constant like this lambda. This is called Lenz's constant. Okay, this is called Lenz's constant. The elastic material is a very important constant. And when the wave propagates through the elastic body, this constant becomes relieved. So you need to understand stress in terms of strain. In generalized Hooke's law, you have understood strain in terms of stress. Same thing, just reversing it. Clear? Okay, I stop it over here. And next two things, I have explained strain energy and resilience for direct strain. You please go through strain energy in shear also. Same concept, same thing. Okay, same thing. Half into sigma square by E you have got. Here you are getting half into tau square by G. Okay, then elongation in tapered bar. Another एक class में थोड़ा बता देंगे. So we are closing this chapter. Okay, with some problem I'll do it. Okay, then we'll close it. Please stop there. Thank you.